Okay, so I think I can start now. It's already 3:06. So I welcome you all to the third week of GATE NPTEL live lectures on mathematical physics questions. So today, in last two couple of classes, we have discussed linear vector space and some basic concept of it, and then few questions related to linear independence of vectors and so on. Those things we discussed in last couple of classes. Now I will dedicate next 2 or 3 classes for linear differential equation. It's a very important topic, and in the first phase of GATE and PTL lectures, I covered not all, but most of the questions which came in GATE exam related to all kinds of differential equation, different kind of differential equation. I've already solved it, and you people can assess that in the first PPT, like which I've shared. But few of the topics were left in the last lectures, and that some special kind of differential equations, like Legendre differential equation, Bessel differential equation, those kind of things. So today I will be covering Legendre differential equations. So I will just start with the basic introduction of these kind of equations, and then we'll solve 2-3 questions which came in GATE exam related to this topic. Okay, so and in the next class we'll move to another class of differential equation and some more classes. So okay, so first of all, before starting with the legendary differential equation, since many of you are new here, joining for the first time, so in this phase, so differential equations are very important. Most of you must be knowing the importance of it. It is very important. It is applied in different fields like in mechanics, in engineering, in science. If you want to study the evolution of a system in time, given some initial conditions and boundary condition, then it can be done using differential equation, heat equation. Like for example, there are a number of applications. Sorry. So there are different kinds of differential equation ranging from ordinary differential equation, partial differential equation and all. But in GATE syllabus, we are mainly deal with the ordinary differential equation, not partial, and that to a different kind of ordinary differential equation. So ordinary differential equation. So different kind of like linear, but and also linear or ordinary differential equation. We'll not be discussing non-linear because non-linear differential equations are very difficult to deal with, and they cannot be solved analytically. So basically, we deal with the linear ordinary differential equation of different order, first order, second order, and so on. Like for example, starting with simple first order, that dy by dx u of y is equal to some zero, some this kind of first order because the order is 1 and the degree is 1, or second order differential equation like you have d2y by dx square plus some d of x dy by dx plus q of x y is equal to 0. Like this is second order homogeneous linear differential equation. So these are different classes of differential equation which we solve, and but there is a special classes of second order linear differential equation. And for example, in this general form which I've written, the coefficient of this d2y by dx square is constant, it is 1. So it's not a problem to solve this differential equation. We can solve it using simple methods. But there is a special classes of differential equation where the coefficient of this second order derivative is not constant. It is some x. It is some variable. It is not a constant coefficient. So those classes of differential equations need to be solved in a different way. Like in the next class, I will discuss like Cauchy, Euler. I can discuss this kind of questions in the first session, but I will again discuss it in the next class. And also there are special kind of functions such as legendary differential equation, which also belongs to these classes of differential equation. So basically, it is a special kind of what is a legendary differential equation? It is a special kind of second order linear differential equation, and it has a huge application in different field of physics. You people must be knowing more than me, like in quantum mechanics, in hydrogen atom problem, and angular momentum. In those places, yeah, these legendary differential equation and legendary polynomials are often used as a solution. So it has a huge application also in different field, legendary polynomials. So these are the special kind of second order linear differential equation, and with following form. Uh, 1 minus x square d2y by dx square minus, suppose I'm just writing one of the form. This is the legendary differential equation. This is the particular form of this legendary differential equation. And since you see there is a x square term coming in the as a coefficient of the second order derivative of y, and x is the independent variable here and y is the dependent variable. So in generally when we solve this kind of differential equation, we use something called power series method, which in your bachelor course you must have done. I won't be discussing this, but just a brief description that how, in what, in this kind of power series method, what we do is that we assume some solution that y is, we assume solution, that solution y is of the form summation r is equal to 0 to infinity exponent some coefficient ar x to the power m minus r. So this is a solution which we assume, and then we just find the first derivative y, which is
Sir,
excuse me, yes.
sir, this formula is when we are having a singular point, right? But the legendary differential equation, there's a sorry, there's a sorry, what's called regular singular point. But in this differential equation, at x goes to plus or minus one, there's a singularity. So why in this case there's singularity present? Then why um, that form of equation is chosen? Can you
You're
explain? I
uh,
tried to find it everywhere, but I couldn't find why the reasoning.
okay, like you're saying that in this, which equation is saying that singularity exists? This particular equation, 1 minus x squared.
Uh, at x goes to plus or minus 1, the coefficients of d2y over dx2 becomes 0.
Okay.
So if that kind of situation arises, we know that it cannot be solved. Uh,
Okay, yeah, it diverges. He was telling that it diverges at x is equal to plus minus 1. So actually, when we solve, I've not gone into the details of the derivation and how you will come around this particular question which I've raised. I will discuss it with you. But in general, I'm just talking about general how we solve this kind of question. So you generally, what's your name? You can just tell me now. Answer who asked the question.
sir, my name is Chaudhary. Chaudhary.
Okay, okay. Okay, George. I will discuss with you in. I will discuss this thing when I will proceed ahead. Okay.
Okay, sir.
Okay. First, let me do this. Okay. So generally, what we do is that we just find the first derivative. We'll find something, and then we'll find the second derivative of this particular equation, and then we just put back these two thing back into this original equation, and we take some coefficients, like whatever coefficients are there, and then we just, in this way we solve the power series method generally. in legendary differential equation also, the derivation part I have not been covering. I think whatever question you asked, Chaudhary, I think that can be dealt with when I'll be doing derivation. If you want me, I will do it in the next class. So what can be done is that when we solve this kind of equation, there are two independent solutions which we get for the legendary equation. And the solutions are very large, so I am not writing, I'm just writing the general form of the solution. Actually, why I'm not discussing very details or derivation, those things, because initially that's not the motive of the lectures, because the main focus is solving questions. But it's good that you have raised this question, and so we can always discuss this. I will dedicate some classes only based on this kind of doubts, where we will discuss all the doubts which you have raised. Okay, so the general form, the solution of the legendary equation is of this form. Okay, and because when you solve this power series, when you solve this legendary differential equation using power series method, you will get two independent solutions. You will get two independent solutions, and hence, because you're getting two independent solutions, so y can be written as the linear combination of these two independent solutions in this form, where p and x are nothing but their legendary polynomials of different orders. Different order when n is 0, 1, 2, etc. And q and x is a legendary function of second kind. So basic thing is that this first solution, which is p and x, legendary polynomials, they always contain the positive power of x. They always contain the positive power of x, and this q and x, the second form of solution, which we q and x, they have also the negative power or something of x, if I'm not wrong. So these are the basic solution which you get of the legendary polynomial equation. And the main focus is this first solution which you get, p and x, which are called legendary polynomials. And they are represented by simple Roderick's formula, like minus 1 to the power n. So this represents the general formula for deriving different polynomials, legendary polynomials of different order depending the value of n. So, for example, n is equal to 0, we'll get 0 order polynomial, which is nothing. We'll just put in this equation n is equal to 0, you'll get 1. For n is equal to 1, you will get something like, just put n is equal to 1 in this equation, solve it, you'll get x. So the p2x, you'll get something like 1 by 2, 3x square minus 1 for n is equal to 2, and for n is equal to 3, you'll get cubic in x 1 by 2, 5x cubed minus 3x. So like these are different solutions graphically if you want to see that. Like for this is one, so first polynomial is just a straight line parallel to x. So it is p0x. The first is a straight line. So p1x will be something like this. P2x is square. So at 0 it will be minus. So it will start from somewhere from there. And then it will at 1 it will become 3 minus 1, 2 by 2, 1. So at 1 it will become 1. So it will go something like this. Similarly, you get different orders. So P3 will be something like this. Oh, sorry. So all the hard work is gone now. Yeah, so this P1 is like this, P2 is something like this, P3 is something like this. So different, if you just plot these polynomials, you will get something like this. So these legendary polynomials are, these are different like order of legendary polynomials. And now, in order to solve the gate questions, you need to remember only, I will tell only couple of, there are number of properties and recursion relation which you will get in any literature. You can just go through them. But in whatever research I've done, like in questions which come in gate exam, one of the most important properties which is required is orthogonality. So orthogonality of legendary polynomial. So that property is that the integral -1 to 1 pnx pmx dx is equal to some chronicle, this is chronicle delta function, which is equal to 0 if m is not equal to n and is equal to 1 m is equal to 1. So there is some constant term also here, which, so this is one of the very important property of the legendary polynomial, the orthogonality. The proof of it I'm not going to do, you can just see in any book. And then another, if n is equal to m, second case, using this orthogonality equation, if n is equal to m, then we'll have dx, which is equal to 2 upon 2n plus 1. So this is another important property, second, and this is first. And then there is another important property which you can keep in mind. Some x to the power n pnx dx is equal to 0, where m is less than n. So this is third. So these are the three important, like these are derived, the second is derived from first only. So basically only two, orthogonality of legendary polynomials and this third one. So these can be derived using different recursion relation also. I'm not talking about recursion relation. Recursion relation means the relation between a different order of polynomials. For example, the relation between Pn to, what is the relation between the Pn with Pn plus 1, Pn minus 1, those kind of things. Those kind of question doesn't come in any competitive exam because those are theoretical questions. They can come in university exam and all, those derivations and all. So I'm not going to derivation of those things. So now what I will do is that I will just give you one, based on these properties. I will just ask you like, okay, this question didn't come in gate exam, but it can come anytime, like this can come. So like the question is, you have to given an integral, the value of the integral -1 to 1 2x plus 1 p3x dx, where p3x is the third degree legendary polynomial. So it's a simple question. So you can just try it and type the answer in chat box. You can use these properties if you want. Straightforward, using one of the property you can solve this. The lengthy way is using Rodrigues formula. You substitute P3 with this. You have the Rodrigues formula. So lengthy method you don't want to do in exam, but you put n is equal to 3 here, and then solve this. But that would be a little longer, not nice way to do. So some people have already answered. Very good. What is S?
Because it is orthogonal property. I use orthogonal property for this.
Okay, good. Yeah, so 0, right? Hmm. Yeah, it's straightforward. So I think I will. So you can just write this as xp3x dx plus minus 1 to 1 p3x dx. So now you know, I've already told in the last, the third property x m pnx dx is equal to 0 where m is less than n. So here m is 1 and n is 3. So this property, using this property, this integral will go out. Similarly, this you can write x to the power 0. So here also n is 0, m is 3. M is 0 and n is 3. So this term also vanishes. So directly using this orthogonality relation, you came to this answer that this answer of this question is 0. So you get this kind of straightforward questions only, where you have to use the property and then solve the question. I think this must be clear to everyone, right? Only one person has answered. What about others? Were you able to do this? Hello?
Yes, sir.
Okay, okay. Okay, now we'll come to a gate question. So this question I didn't solve in the first, like I gave it as a homework, but in the first session, but I didn't solve. Now this, in this session, I'll just solving this. So the question is, the points where the series solution of the legendary differential equation will diverge are located at. So you have been given some standard legendary differential equation, and then they are asking that at what point the solution of this equation will diverge. Now, you can solve this. I am also solving. You can just proceed by just knowing the general form of the solution. The general form of the solution of the legendary differential equation is this, where p and x is, as I said, so p and x, these polynomials will always have some positive value of x, okay, x square, x, then those things. So, but the q and x is legendary function of second kind. It's little complex, and the first two order, the q0x is represented by this minus 1. So these solutions, as we know, that the second solution of this legendary differential equation, which has q and x, 1x, this will diverge, like when you put x is equal to 1, this term will go out. It will become log of infinity, which is not defined. Similarly, when you put x is equal to minus 1, then also it becomes log of 0. And log of 0 is nothing but what? It is also minus infinity. Like it is also not defined, because you know that log of 0 if is
Sir, can you
x.
repeat once again? 0x from
So
the Q0x.
qx.
What you have told from the Q0x? Can you repeat?
Yeah, yeah. For q0x, what I'm saying is that the first two solution, like the first two terms of this q and x, that q0 and q1, are given by these two equations, half of log 1 plus x and 1 minus x. It can be written in this form. And similarly, q1x can be written as x by 2 log of 1 plus x upon 1 minus x minus 1. So when you put this back into this original equation, then you will have the solution will diverge. Diverge means it will be not defined at two values. For example, when you put x is equal to 1, then this will become log of 2 upon 0, which is not defined. So solution is diverging at x is equal to 1. similarly, at x is equal to minus 1, it will become log of 1 minus 1 upon 2. So log of 0, and log of 0 is also not defined because log of 0 is supposed as x, so e to the power x is equal to 0, and you know that e to the power minus infinity is equal to some, so it is also not defined. So for these two values, the solution is diverging. You're getting infinities in the solution. Hence, you can just say that out of these four options, the solution is diverging at 2 points, 1 and minus 1. How you came at these values, I will, if you want, I will cover this in derivation part, that how you arrive at these two values.
Sir,
Hmm.
can't we solve the question from the differential equation itself? At x goes to plus or minus 1, there's the coefficient of d2y over dx2 becomes 0. So that must be the points where the functions becomes not analytic.
Okay, okay.
So do I really need to write the equations,
Yeah.
or I can? This is the question I was asking before.
Oh, okay.
It becomes minus 1 and plus 1, but why the equation?
Okay, okay. So you're just okay. So you're talking about when you put okay, from this coefficient will come 0. So is it clear or not? Or if you want me to clear it, I will do it in
No,
next
no,
class.
sir. Actually, that was my question. If minus 1 and plus 1 becomes the point where the solutions become divergent,
Yeah.
then why we choose the solutions of the regular singular point? The initial form that you took
Okay,
was
okay.
because of the regular singular point. But if
Yeah.
this function becomes a minus 1 and plus 1 divergent, then why this form was taken, or that was my question. But because the form, sometimes we take different form.
Yes, yes,
So
yes.
why that form was taken? So that was my question. That was my question.
Okay, Chaudhary, what I will do in next class now, first thing I will clear this your doubt. Is it fine? So right now
Okay, sure.
yeah, right now I won't be answered like judicially. So in next class I'll be doing it. Okay.
Yes, sir.
Okay, thank you. Okay, so now there was another question which came in GATE 2010. So the question was that given the recurrence relation for the legendary polynomials, so as I said, you don't need to remember this recursion relation they will give in the exam. So this is the recursion relation where they are giving a relation between the legendary polynomials at different values of n. The Pnx is related to Pn plus 1 and Pn minus 1. So which one of the following integrals has a non-zero value? So you have to find that which of the following integral has non-zero value. So in order to solve this, what you can do is that you can just solve individually. You will use the orthogonality property. So you can just check one by one. So what you will do is that first you will check or take option 1. So option 1 is, you can write this option 1 as x p n x times, you can break it in this way, x p n plus 1 x dx. Okay. Now when you just you can now use this recursion relation, and you can write x time p n x. You can just substitute from here. X time p n x is nothing but n plus 1 p n plus 1 x upon 2n plus 1 plus n p n minus 1 x upon 2n plus 1. So you just use this relation given in the question paper only, and you substitute the value of p and x. Similarly, you can just also substitute the second this also. So you just replace n with n plus 1 in this equation. So because there is n plus 1 here, so you just replace n with n plus 1. So what you will get is n plus 2. You put n is equal to n plus 1, so n plus 2 will come here also, upon 2n plus 1 will become 2n plus 2 plus 1, that is 3, plus you will get n plus 1. P of n plus 1 minus 1 will become Pn of x upon 2n plus 3 times dx. Now what you will do is that you will just multiply all the terms. So the first term will have some constant value of n, pn1 plus 1 times pn plus 2, and multiplying this with I'm multiplying with these two terms. So these two term has pn plus 1 times pn plus 2, and we know that we have some constant term, and pn plus 1. Now these, we know that by orthogonality this will turn out to be 0. Similarly, we'll have another term with some constant c2 will come, which is a function of n. Second will become pn plus 1 times pn. This will also be 0. This will also be 0. Similarly, third term will also be 0 because pn minus 1 pn plus 2. And fourth term will also be 0 because pn minus 1 times pnx. So all the four term are all the four term using orthogonality property are coming out to be 0. So the first option is not correct. It has 0 value. Similarly, you will try second also, you will get something similar only. If you can try third option, then you'll get, suppose, let us try third option. So you just write it. It is x times pnx whole square. This is square. So you can just break it similar way. X pnx dx, and then just use the same recursion relation which is given in the question paper. This. So what you will write is you will get n plus 1 pn plus 1 x upon 2n plus 1 plus, okay, there's only one x here, so there'll be only one x, okay, and n pn minus 1 upon 2n plus 1. This will be divided by pnx. Now again, when pn plus 1 will multiply with pnx, it will become 0. And similarly, pn minus 1 times pnx using orthogonality property will also be 0. So this will be also be 0. Now let us try fourth option. It is option D. Option D has x squared pnx and pn plus 2x. Squared pnx n plus 2x. Now when you solve this, you same property, you will just break in two parts. X pnx x pn plus 2 dx. So when you solve this, the first one you can just write n plus 1 pn plus 1 upon 2n plus 1 plus n pn minus 1 upon 2n plus 1. You can write this. The second, this you can just write, you can just replace n with n plus 2 in the original recursion relation. So you'll get n plus 3 pn plus 3x upon 2n plus 5, because remember there is 2n plus 1, you're replacing n with n plus 2, so 2n plus 4 plus 1 is 2n plus 5, plus n plus 2, and pn plus 2 minus 1 is what? Pn plus 1. Hope I'm not making any mistakes. Now you just multiply this. First will be 0 because n plus 1 and n plus 3, so it will be 0. This will not be 0 because there is pn plus 1 and n plus 1. This will again be 0, and this will again be 0. So we have got one term which is non-zero, which is n plus 1 times n plus 2. 2n plus 1, 2n plus 5, Pn plus 1 whole square dx. And the solution is what? This term, let me call this as some constant with a function of n. And this integral minus 1 to 1 Pnx square dx is nothing but, as I discussed in the properties, it is 2 upon 2n plus 1. So, and here n plus 1 is here because it's n plus. So 2 upon 2n plus 1 will be plus 3, which is not equal to 0. So only fourth option is the one which has the non-zero value. So among all these four options, using this recursion and using this orthogonality property, you found out that this fourth integral does not have zero value. It has a non-zero value. So you can just take that. So this type of questions, I can find only two questions, two questions in the legendary equations from last 20-year paper. So if other questions come also, they will also follow the same pattern. They will just use these properties, and most probably they will. And also what Chaudhary told, that this doubt I will clear in the next class. I think I will be clearing in next class first. Then I will proceed to the topics. We still have some time, so what I will do is that I will just cover theory of. I will take 10 minutes, and I will not solve question, but I will. In the starting, I discussed something like Cauchy second order differential equation. So yeah, Siddhartha has already answered the question. Good, option D. So those, I think I will just see how many of you are there who attended first phase. I think 3-4 people are there who, and rest majority of you are new, so it's good to cover that topic also. So what I will do is that there are different kind of second order differential equations. So one of the special kind is called the second order uh, linear differential equation called Cauchy Euler ordinary linear differential equations. Okay. And they have this form: x squared d2y by dx square plus x times dy by dx minus m square y is equal to 0. So this is a special form of second order linear differential equation, and which have a non-constant coefficient in front of x, the second order derivative. So in order to solve the question, what you do is that I will just common approach. You assume that this independent variable x is some exponential time t. You just have to assume this, and then you just take derivative of it. Basically, our main motto is to reduce this to reduce this equation in such a form where the coefficient of the second order derivative is constant. So how to make this coefficient constant? So for that we have to do this assumption. Dx by dt will become e to the power t, or by using chain rule. Therefore, dy by dx will become 1 by et dy by dt. Et is nothing but x. So you take here, so it will become x dy by dx is dy by dt. So this is equation 1, this is 2. So this x dy by dx is nothing but dy by dt. Similarly, if you just take another derivative of dy by dx, this is d2y by dx square. So you can write this as dy by dx of dy by dx is nothing but 1 by et dy by dt. Again chain rule. And dt by dx is what? 1 by et. So it will become somewhere like 1 upon exponential t d by dt of this. So you apply product rule. So you will become 1 by et d square d2y by dt square minus 1 upon et. So you just, because e to the power minus t, so differentiate e to the power minus t, you will get minus 1 upon e to the power t and dy by dt. Now you can take e to the power t common, and there is already one e to the power t here, so it will become e to the power 2t d2y by dt square minus dy by dt. So, and when you take e to the power 2t here, so on the left hand side you will get this. And e to the power 2t is nothing but x square. You square both sides. So x square, the first term which we wanted to replace, this non-constant coefficient can be replaced by this, which has constant coefficients. Okay, so you just replace this. So you just use 3. You just use 3 and 2 in 1. Then you will get d2y by dt square plus dy by dt. Sorry, minus dy by dt. And x dy by dx is nothing but dy by dt. So this will cancel out. Plus minus m square y. Minus m square y. So see, you have just reduced the problem into simple second order linear differential equation, and now this is easy to solve. We just assume that d operator is dy dt, so you can just write this as d square minus m square. I've just assumed, we can assume that this differential operator dy dt can be represented by capital D. So d square minus m square times y is equal to 0. So for the complementary function, you just d square minus m square is equal to 0. You just put, you get d is equal to plus minus m. And the solution, we have two distinct real roots. So the solution will be something like y is equal to c1 e to the power, let's say m1t, first root is let not m1t, let's say r1t plus c2 e to the power r2t, where r1 and r2 is nothing but r1 say is m and r2 is say minus m. Okay, so your solution is become c1 e to the power mt plus c2 minus mt. But your t is nothing. You have to replace t with again x. So since x is equal to et, so x to the power m is equal to exponential mt, and x to the power minus m is equal to minus t. So we can just use this. So it will become c x to the power m plus c2 x to the power minus m. Okay, so we got two independent solutions, x to the power m and x to the power minus m. These are like two independent solutions of Cauchy linear differential, second order linear differential equation. Okay, and yeah, so there are a couple of questions, one question I will solve, and one question I already solved in the last session. So I will solve in the next lecture. And first I will clear this doubt, and then I will solve one question related to this this topic, and then I will move to Bessel kind of functions, and then we'll see that in what we'll do in next class. So this is clear. This is general way how to solve this second order. Whenever you see this kind of question where you have this x square term coming in this, you have to follow this approach in order to solve the differential equation. So okay, hello, is this clear? Hello. Any doubt related to this second order Cauchy-Euler differential equation? Oh, so I don't see any doubts. Okay, it's clear. So, okay, so if there are any questions related to questions I've solved, you can ask. Because I don't see like any questions. Okay, so in that case, we can end today's class. Okay, so if there are more questions, we can end today's class. Thank you.
Thank you, sir. Thank you, sir.